Hello everyone, my name is Arash Hashemi. I'm a research engineer at the University of Waterloo. I'm also affiliated with Waterloo Artificial Intelligence Institute. Today, I'd like to present our recent simulation study with Professor John McPhee on assistive sliding mode control of a rehabilitation robot with automatic weight adjustment. To motivate this research, cerebral vascular accident or stroke is the leading cause of permanent disability. Among stroke incidents, cases related to the upper extremity are more common. Rehabilitation programs have been shown effective in restoring neuromusculoskeletal related functions and exploiting brain neural plasticity. Research has shown that intensive repetitive practices can expedite the recovery. These practices are administered by a therapist working with a single patient. Given this one-to-one interaction, the manual therapy is very labor-intensive and costly, and considering the increasing number of patients and the limited number of therapists, it might not be a feasible solution in the future. Fortunately, robotics can be used to automate these tedious activities. In addition to the automation, the data from measurement devices on these machines can be used to quantitatively and objectively evaluate the patient progress. With recent capabilities of virtual reality devices, robots can also be equipped with VR systems to make the rehabilitation more engaging for the elderly population. As a result, robots are a good complement to traditional clinical therapy. In terms of the mechanical design, rehabilitation robots are categorized into exoskeletons and end effector type robots. You can see our robot at the bottom right. Aside from the mechanical design challenges, the controller design is a fundamental challenge in the field. Tracking performance, safety, and patient comfort are among the considerations when designing a controller for rehabilitation robots. Sliding mode control is a powerful method, since it can handle nonlinear dynamics and is insensitive and robust against model parameter uncertainties on model dynamics, sensor noise, and disturbance. From the three rehabilitation modalities in the field, we have employed a model-based assistive control approach. In the assistive category, patients have restored some of their motor functions but still cannot perform the tasks independently. In this case, the robot provides the remaining required torque. Recently, automatic tuning approaches are investigated. In the field of rehabilitation robotics and assistive devices, most of the studies have focused on high or mid-level controller tuning, like impedance and admittance controllers. However, low-level controllers require the same attention since they determine the tracking performance. Moreover, the previous studies have mostly investigated exoskeleton devices, focusing on the assistive capabilities of these devices. In other words, the goal has been on decreasing the user effort and engagement. On the other hand, there is not much research on tuning the controllers of end effector type robots with rehabilitation purposes that promote user engagement. In addition, these studies have employed online tuners with human-in-the-loop testing, which can cause major safety concerns in the field of rehabilitation due to the interaction of patients with untrained tuners. Hence, simulation studies with offline tuners can mitigate this problem. Our robot is developed by Quansor Company and Toronto Rehabilitation Institute. A force torque sensor is also mounted on the end effector in our group. The robot itself is a parallel 2 degrees of freedom 4 linkage mechanism. It is fully actuated with 2 DC motors. The joint angles are measured by 2 optical encoders. The patient grabs the end effector and the robot provides upper extremity planar rehabilitation practices in the horizontal plane of motion. The governing equations of motion are obtained by Lagrange method and are coded in MATLAB 2021. Because of the planar structure of the robot, the equations only include inertia and Coriolis terms and not the gravity term. The human torque is considered as a disturbance term in this equation. The following sliding surface is defined for the SMC based on the joint angle error. The controller consists of two terms: a low frequency equivalent term which derives the closed loop system to the sliding surface, and a high frequency stabilizing term which rejects the disturbance. The original formulation for the stabilizing term includes a discontinuous sine function. Coupled with the high-frequency nature of this term, the discontinuity leads to chattering that causes safety issues and can damage the motors. For this purpose, we replace this term with a smooth continuous tonnage function. Note that the final controller has 3 tunable weights. In contrast to previous studies who considered a generic disturbance like sinusoidal or impulse functions as the patient torque, in this research we formulated the central nervous system controller. We used a hierarchical computed torque PD controller to have a combination of feed-forward feedback terms. We considered a 2 degrees of freedom planar model as the human arm with elbow flexion extension and shoulder horizontal abduction adduction. To consider the muscle stiffness and viscosity, we included the passive term of muscle torque generators. In order to simulate the stroke condition, we adjusted the CNS weights to account for low muscle activation. We modeled human slacking by reducing part of the human torque in the previous simulation cycle, which is one completion of the predefined trajectory, from the current cycle whenever the tracking error is less than a certain amount. We use a forget factor of 0.01 for this purpose. Plus, we simulated the rehabilitation progress by increasing the CNS weights at each cycle whenever the human applies more average torque than the initial average torque. We use genetic algorithm optimization for our offline tuner with 20 generations and 20 generation population. For the cost function, we included the tracking error, the robot torque and torque rate, and the negative of the human torque. The first 3 terms result in good tracking performance with low smooth inputs, and the last term promotes human engagement. For future online experimental implementations, the force sensor data can be used to estimate human torque. Note that our assistive modality is applied implicitly by finding the optimal weights. Here you can see the optimization results. We considered a circular trajectory tracking scenario. On the bottom left, you can see all the weight combinations used by the optimizer. The blue weights have a lower cost. On the top right, you can see the population costs for each generation. As shown, all the population costs converge to the optimal value as the optimizer proceeds to final generations. The optimal weight setting has the least cost compared to 7 manual weight settings as shown on the bottom right. The human-robot interaction provides a much better tracking performance compared to human-only tracking. Also, the robot inputs have low frequency and are well within the 10 Nm DC motor limits. To conclude, in this study, we simulated the interaction between the subject and a rehabilitation robot. We provided a realistic simulation by formulating the CNS controller, considering muscle components, and modeling post-stroke effects and rehabilitation progress. Our GA-based offline tuner could provide the optimal weights based on minimizing the tracking error, robot torque and torque rate, and maximizing the human engagement. Modeling the stroke effects and rehabilitation progress for realistic human-robot interaction simulations and using automatic tuners for rehabilitation purposes are the main contributions of this research. Note that our study is a proof of concept for automatic tuners in rehabilitation. More advanced tuners can be considered in the future. For instance, since our GA tuner is not explicitly state-dependent, it cannot be used as an adaptive tuner. Having said that, instead of using random initial weights as done by previous assistive studies, the results of this research can be used as the initial weights of other online tuners. This approach minimizes the mentioned safety concerns of previous studies and enables the use of more advanced methods with fast convergence. Our main research is on model-free reinforcement learning, and we will apply this approach for adaptive tuners in our experimental implementations. You can check the PDF version for the references used in this presentation. Thank you very much for your attention. You can reach out to us for further discussions about this or other projects.